Hi guys, this video is about improper integrals. I'm going to start this the same way I typically start my face-to-face class over improper integrals. Let's say I'm given this integral. Well, first I apply the fundamental theorem of calculus. Antiderivative of 1 over x is natural log of the absolute value of x. And we'll evaluate that from x equals -2 to x equals 4. So we plug in the upper limit and substitute in the lower limit. Of course, you're taking the absolute values of those numbers, and then you subtract. Or we'll just, absolute value of 4 is 4, and the absolute value of -2 is 2. And if you want, you could use log properties to simplify. Log of a minus log of b is log of a over b. So I get this. This is wrong. I made a mistake somewhere. Do you guys see the mistake? Do you see? I mean, it looks right, doesn't it? I just took the antiderivative, plug in 4, plug in -2, subtract, did a little algebra to simplify, and then I got the answer. But it's wrong. The reason that it's wrong is that this is an improper integral. I can't apply the fundamental theorem of calculus this way because the fundamental theorem of calculus does not apply in this case. Now, in different textbooks it's stated slightly differently. In Thomas's calculus, 13th edition. He says if the function f of x is continuous on the interval from a to b, and I will tell you that it's not necessary that it be continuous, but it has to be something like that. We'll leave that for another course, but in Thomas's book, he says if f is continuous on the interval from a to b, and capital F is an antiderivative of f, that just means that if you take the derivative of capital F, you get little f back. Then the integral from a to b of f of x dx is f of b minus f of a. So you take the antiderivative, you plug in b, you plug in a, and you subtract, and that's your answer. That doesn't actually apply here. So let's look at a graph to see why. Y equals 1 over x is a function that looks like this. This function is undefined when x equals 0. So I can't plug in x equals 0. X equals 0 is not in the domain of this function. But I can plug in numbers that are very close to 0. So of course I could substitute in 1. When x equals 1, y is 1 divided by 1, which is 1. Or I could substitute in x equals 1/2. Now 1 divided by 1/2, so let's just make a table of values to make this more explicit. If I'm dividing by 1/2, that's the same as multiplying by the reciprocal. So I've got 1 times 2 over 1, so I just get a 2. Oops, it should be there, not there. And then at 1/3, do you see what happens? I'm dividing by the reciprocal, or dividing by a fraction, so I multiply by the reciprocal again, and this time I get 3. So that's at 1/3. And at 1/4, I get 4, and at 1/5, I get 5, and at 1/10, I get 10, and at 1/100th, I get 100, at 1/1000th, I get 1000, And so the y values on this graph are getting larger and larger. as we get closer and closer to 0 from this side. Now, as the x values get larger and larger, so this is 1, I substitute in 2, the y value is 1/2, substitute in 3, the y value is 1/3, substitute in 4, the y value is 1/4, and you just keep going. You substitute in 100, you get 1/100th. It's a very small fraction. So the y values are getting close to 0 as x goes to positive infinity, and as x approaches 0 from the right, the y's are going to positive infinity. Now, if I'm on the left of 0, so at 0, this is undefined. Can't do that. Don't plug in 0. Can't divide by 0. But if I substitute in -1/3, -1/2, and -1, we're going to see the same patterns we saw here, but instead of dividing by positive, I'm dividing by negative. So 1 divided by -1 is -1. And -1/2 divided by, or 1 divided by -1/2 is -2 when we multiply by the reciprocal. And 1 divided by -1/3 is -3, and so on. So as we get closer and closer to 0, from the left this time, the y values are getting larger in magnitude, but they're getting more and more negative. So the graph is going to look like this. Now if I substitute in -100, I'm going to get -1/100, -1/100th. That's small. It's a little bit less than 0, but it's very small. So our graph is going to look like this on this side. And you see this problem? This is asking me for an area under the curve between x equals -2 and x equals 4. So when x equals -2, the y value should be -1/2. The region I'm talking about is this region. It starts at -2 and goes to 0. And then you pick up on the other side. We have the area under the curve between 0 and 4. The range is unbounded here. The y values go to -infinity for this piece, and the y values go to positive infinity for this piece. So we have an unbounded area, so fundamental theorem of calculus does not apply. Now, it might be the case that that area is finite. But since the fundamental theorem of calculus does not apply, we can't just do this. This is not legal. Don't do this. We've got to do something else. So this is one of two types of improper integrals. Here we have an unbounded area. And I'm just going to write unbounded range, because the y's go to -infinity and positive infinity. The other possibility is we could have an unbounded domain. So here's another type of improper integral. Let's say you have the integral, well, even same function, from 1 to infinity of 1 over x dx. So the graph is going to look the same basic shape. I'm not going to be so detailed about the x and y values anymore. When x equals 1, y equals 1. And I'm looking at the area under the curve from 1 to infinity. So we've got an unbounded area here, and we've got an unbounded area here. And since the area is unbounded, this is because of the unbounded domain. And fundamental theorem of calculus does not apply. We were told that f had to be continuous on a closed interval from a to b. And this function's not continuous on the closed interval from -2 to 4. This function has an infinite discontinuity at x equals 0. So you've got one type of improper integral that results from infinite discontinuities. Or if you prefer, you could just say the graph of the function has a vertical asymptote in the interval from a to b. So that's one type. And then the second type, actually we're going to do it in the reverse order. We're going to do this one first. This is the second type. The first type involves unbounded domains. So an infinite upper or lower bound. If I went from negative infinity to a constant, or a constant to infinity, or negative infinity to infinity, we're going to call those infinite bounds. And I'm just going to say upper or lower bounds for emphasis. So those are our two types. In both cases, the fundamental theorem of calculus does not apply. I'm going to call this one type 1, and this one type 2. We're going to focus on type 1 first, and then we're going to look at type 2. But remember, it's improper if you see a negative infinity or infinity. That makes it an improper integral because of the infinite bounds. And it's also an improper integral if this function has a vertical asymptote on the interval from a to b. Or equivalently, this function has an infinite discontinuity on the interval from a to b. And it could happen at a point on the interior of the interval, like it did with this one at x equals 0. It could happen at a, it could happen at b. Either one is fine. But notice that when I draw my picture, I've got this unbounded area where y is going to negative infinity, and I have an unbounded area here where y is going to positive infinity. And then this one, I've got an unbounded area where x is going to positive infinity. So those are our two types. So these are improper. We can't apply the fundamental theorem of calculus, but if we define them in a slightly different way, it turns out sometimes we do get a finite area here. You know, that area minus that area, that might be 17. Who knows? Or it might be infinity or negative infinity. Actually, if one of those is infinite, we say that the improper integral diverges. And we'll talk about that in a little bit more in a minute. But there are lots of possibilities here. We might have infinite area under this curve, or we might have finite area. And that is a little bit difficult to wrap your mind around, but just think about it this way. If I'm adding something very, very, very small every time, the sum might approach a finite number. And we'll get back to that actually when we talk about sequences and series later this semester. So let's just talk about type 1 integrals, type 1 improper integrals. So you've got three types of type 1 improper integrals. You might have the integral from a to infinity of f of x dx. We're going to define that to be a limit. All improper integrals are defined as limits. The problem limit for us is that b, that upper limit, which is infinity. So I'm going to replace that upper limit with b, and then take the limit as b goes to infinity of the integral from a to b of f of x dx. So all improper integrals are written as limits, and this is how you write this one. You might say, well, what does that mean, Miss Townsend? Well, what that means is this I can't do. This the fundamental theorem of calculus does not apply to. But this is something the fundamental theorem of calculus applies to, provided that f of x is continuous on this interval from a to b. So we're assuming this function is continuous from a to infinity, so this is going to be equal to this. And maybe it looks like 1 over x again. I don't actually know what it looks like, but maybe it does. Maybe it looks like this. We want to know what the integral is, or that unbounded area is, from a all the way to infinity, like all the way out there. We want to know, is that area finite? And I know it seems impossible, but I'll show you a case when that area is actually approaching a finite number. But we can't do that using the fundamental theorem of calculus. So this is what we do instead. You say, aha, I can't use the fundamental theorem of calculus with that, but I could choose this other point B and find that area, and then I could see what happens to that whole quantity as B goes to infinity. So we'll have a number here, and then when B is 10, we'll get a different number. When B is 100, we'll get a different number. When B is 1,000, we get a different number. We want to know, as B goes to infinity, does that area approach a finite number? If it does, if this limit is finite, we say that this improper integral converges to its limit, whatever that limit is. I'm just going to call it L. You say, okay, well, what does that mean? Well, in some limiting sense, this unbounded area here is L. It has area L. Now, if we go to all that trouble and we get something that's going to infinity, well, then this area, we would say that unbounded area is infinite. So if the limit is finite, if it exists, we say that the integral converges. Left off the word integral. Improper integral converges to L. If for some reason the limit does not exist, maybe it's infinite, maybe it's negative infinity, maybe it's something odd like sine of B just oscillates for all time, for all B. If the limit does not exist, we say the improper integral diverges. Now, if it diverges and the limit is infinity, we will say, and I'm going to put this in quotes, L equals infinity, because infinity is not a number. Not in this number system anyway, not in the reals. We'll say the integral diverges to infinity, and we'll interpret this as infinite area. Or, if the area is below the x-axis, or we've got some area above and some area below, and then the limit turns out to be negative infinity, we'll say that this diverges to negative infinity. Now, technically, both of these limits don't exist. They just don't exist in a very special way, such a special way that it's meaningful to talk about this area growing without bound, or this area being infinite, but then also below the x-axis, the net area being negative. So this is our terminology. The limit doesn't exist, the integral diverges. If the limit does exist, we're going to say that that's what the area is. That's the area of our region. Okay, so if the upper limit is infinity, you do this. Now, if the lower limit is infinity, negative infinity, the problem is the lower limit. I usually like to have an a there, so I'm going to let a go to negative infinity and evaluate the integral from a to b of f of x dx. And this used to be a negative infinity. I'm going to replace it with an a. Picture for that looks a lot like the picture for this. Maybe it looks like this instead. But I'm going from negative infinity to b. We want to know what this area is. So what we do is we find out this area, because this is proper. With this, I can use the fundamental theorem of calculus. All the nice math that I learned at the end of Calculus 1, it applies here. Actually, all the nice math we learned earlier in this chapter applies here. So I can find this. And then I say, okay, well, what happens if a is negative 10? And what happens if a is negative 100? And what happens if a is negative 1,000? What happens to this quantity, this formula for area, as a goes to negative infinity? Is it a finite number? If so, the improper integral converges to that number. Does the limit not exist? We say it diverges. Does it not exist in a special way? We might say it diverges to infinity or it diverges to negative infinity. Now, those might seem like the only possibilities, but there's actually a third possibility. And we'll work a problem like this. Maybe you have the integral from negative infinity to infinity of f of x. Obviously improper. I've got two problems, the lower limit and the upper limit. This is easy enough. You just split it. You can pick any x value in between negative infinity and infinity, which is literally any x value you want, any real number. As long as this function is continuous on the entire real line, this is legal. So you're going to split this into two integrals. You're going to have the integral from negative infinity to that number, I'm going to call it c, plus the integral from c to infinity of the function. And this one can be written this way, and this one can be written this way. If this converges, then I have to work this out and find out if this converges. If they both converge, this guy converges, and it converges to the sum of these two guys. Now, if this one diverges, we're done. If this limit does not exist, after I write it as a limit and I do all this work, if this limit does not exist, then this one automatically does not exist. It's not possible for you to get negative infinity over here and positive infinity over here and for us to add them together and say, oh, the area is 0. We're not going to do that. Not in this class. There is something, yeah, there's a special value, it's a principal value of an integral that they talk about in physics, where they do things like that, where they let the negative infinity and the positive infinity cancel out. But mathematicians don't like that. They say, if this is improper, or not improper, if this limit does not exist, then this one automatically does not exist. If this diverges, this diverges. If this one converges, you got to do the more work. If this one, then check this one out. If this one converges and this one diverges, then you're done and this one diverges too. So if either one diverges, this guy diverges. Yes, let's practice some problems. Just have an example or two. I'm going to pick a pretty simple example integration-wise because I just want to focus on improper integrals. So let's say we're looking at the integral from 1 to infinity of 1 over x squared dx. Now, visually, this is what I'm doing. 1 over x squared looks a lot like 1 over x. The slope is a little bit different. It looks like that. But if I take a negative number and I square it, it's going to be positive. So I get 1 over a positive number, and instead of having the branches up here and down here like they do with 1 over x squared looks like that. It's supposed to be completely symmetric about the y-axis. Now, we're concerned about this area starting at x equals 1 and going to infinity. So I'm going to start here, and I'm going to go all the way out there. The question is that area finite? Well, I don't know. This is an improper integral. It's not playing by the rules. I got to do something else. So I'm going to define this as a limit. All improper integrals are defined as limits. And I always look at this and I think about the problem x value. Now there's not really a value here, is there? The problem is that x's go to infinity. So we're going to write this as a limit as b goes to infinity, b because it's the upper limit. And we're going to keep everything else exactly the same. So that's your first step. You want to write the improper integral as a limit. And we're still focused on what an improper integral is and how we evaluate them. So with that in mind, let's go back to our picture. The fundamental theorem of calculus does not apply to this. But if I look at 1 over x squared on an interval from 1 to b and b is finite, The fundamental theorem of calculus certainly applies to that. I can calculate that for any b I want. Not b equals infinity, because infinity's not a number. You can't just plug in infinity. We're not those kinds of people. We don't just do that. We're going to, but this is a region where the fundamental theorem of calculus does apply. Not just a region, but a function where the fundamental theorem of calculus applies on this interval. 1 over x squared is continuous on the interval from 1 to b for any b. So, I can just use the fundamental theorem of calculus to evaluate this now as a function of b. So, we're going to apply the fundamental theorem. It's one of the fundamental theorems, I know. Part 2, part 1, depending on the book. And remember how we do that. First thing you do is you take the antiderivative. Well, don't tell me that's natural log of x squared. It's not how it works. If that exponent is anything other than a 1, it's not a natural log. If it's anything other than a 1, you got to bring that up to the numerator. And this is just a little algebra review. Remember, if you have 1 over x to the n, that's x to the negative n. We're going to use this rule over and over again. If that exponent is anything other than a 1, do this. And now we'll take the antiderivative, because I can just use the power rule. I'm bringing my limit along so that everything is nice and equal, but I'm not really doing anything with it. I'm just sort of focused over here. If I could, I would just gray all of this out and focus here while I'm applying the fundamental theorem of calculus. So we take the antiderivative, add 1 to the exponent, divide by the new exponent, and then substitute in 1 and b and subtract. So we're applying the fundamental theorem by first computing the antiderivative, and then of course you want to do f of b minus f of a. And these are steps, not subtraction signs. Okay. I still don't think in terms of negative exponents, so I'm going to go ahead and use this guy to rewrite it again. That x to the negative 1 is going to give me an x in the denominator. That negative 1 in the denominator, it can be pulled out front. So this is really negative 1 over x. And I'm going to substitute in b and 1 and subtract. So I get negative 1 over b minus a negative, so that's minus negative is a plus, 1 over 1. And I get this. Now we can simply just evaluate the limit and be done. That's exactly how I would finish this problem. But I want to focus on what's actually happening here. This is the area under the curve for a given b. So I'm going to make a table. If b is something other than 1, let's say it's 2. We get the integral from 1 to 2. It turns out that that area is going to be 1 minus 1 over b every time. So the area is going to be 1 minus 1 half, and we're going to get an area of 1 half when b is 2. That's what happens. You say, well, b is supposed to go to infinity. I know. We're getting there. So then we'll substitute in 10 now. Well, what do I have there? So I get 1 minus 1 over 10. So it's 1 minus 1/10 is 9/10. Going to be left over. That's our area. You say, okay, what if I substitute in b equals 100? As I go farther and farther and farther out, is this approaching something? What is it approaching? Well, 1 is 100 over 100. So 100 over 100 minus 1 over 100 is 99 over 100. Look at that area. 0.99. Substituting b equals 1,000. Go from 1 to 1,000. Area under the curve from 1 to 1,000. Totally legal. Fundamental theorem applies. And I get 999 over 1,000. Or 0.999. That's my area. Do you see what's happening to the areas? I've got, let's look at it in decimal form, 0.5 and 0.9 and 0.99 and then 0.999. And you can bet if I put 10,000 down, you get 0.9999. Just keep adding zeros. You can keep adding nines. Do you see that we get infinitely close to 1? And the farther we go out, the closer this area gets to 1. I hope that you see that. It's just like taking a limit as b goes to infinity, Calc 1 style, numerically, using a table of values. So now let's do it algebraically. What happens to 1 minus 1 over b as b goes to infinity? Well, 1 over b, or 1 over something really large, like 1 over a million, that's very small. And as this gets larger and larger and larger, this gets smaller and smaller and smaller. So this guy goes to 0. And that last step is to evaluate the limit. And the answer is 1. You might say, Miss Townsend, what does that mean? That means this red area, the area that I tried to draw at the beginning and couldn't go on forever, but I wanted to, is supposed to represent that area starting at 1 and going all the way to infinity. It's the area given by this integral from 1 to infinity of 1 over x squared dx. We're going to say that's 1. In some limiting sense, as I get farther and farther and farther out, we're getting closer to 1. Because it looks like the farther I get out, the smaller this thing is that I'm subtracting. There's just this, it's going to be 1 minus this tiny, tiny area over here. And the tiny, tiny area is going to 0. So in the limit, it's basically gone. It is gone. And we just get 1. Okay. So that is an improper integral of type 1. Type 1 because it has infinite bounds, where the area under the curve happened to be finite. Let's do one where it's not finite. All right, 1 over x looks a lot like 1 over x squared. But when x is negative, it's down here. When x is positive, it's up here. Slightly different slope. We're interested in the area from 1 to infinity, all the way out. Okay, we see right away this is improper because of the upper limit right there. So we're going to take the limit. The upper limit's the problem. So we're taking the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. So first step, always with these, first step is write the improper integral as a limit. Even if I don't know what it looks like, even if I have no sense of the graph, this is equal to this. The fundamental theorem of calculus does not apply to this, but it does apply to this. So I can just do this and then take the limit of the answer. And that's going to tell me something about that area of that region right there. Okay, so I've written the improper integral as a limit. And now I'm just going to do my next thing, which is applying the fundamental theorem of calculus. So we need to anti-differentiate. So that means we're going to find capital F, and then do f of b minus f of a. Easy breezy, super simple. So bring the limit as b goes to infinity down. Antiderivative of 1 over x. That is an x to the first. That's a natural log of the absolute value of x. evaluate from x equals 1 to x equals b. And we get this. Natural log of the absolute value of b, b is going to infinity, so it's positive, so we can just say b, minus the natural log of the absolute value of 1, which is 1, and natural log of 1 is 0. So I just want to know what happens to natural log of b as b goes to infinity. Now this might be something you've forgotten. It's okay if you have. This is what the graph looks like. It's probably been a little while since pre-calc or college algebra. Y equals natural log of x looks like this. When x equals 1, y equals 0, and it just keeps growing. Now my picture is a little bit misleading. It looks like it's growing kind of fast. It's actually not growing very fast at all. But as x goes to infinity, the y values go to infinity. So instead of an x, I've got a b, but it's exactly the same principle. As what's inside goes to infinity, natural log of something really large is a really large number, theoretically. So we get infinity. So this area, it's not finite, it's infinite. So we're just going to call it infinite area. And we would say this integral that we started with diverges in a special way to infinity. So we wrote the integral as a limit. We need to know how to do that. It's the very first step in all these problems. Then we have to apply the fundamental theorem. Now some people get bogged down right here, just trying to get from here to here. So you've got to use your basic rules for anti-differentiation, maybe one of those 9 techniques from section 8.1, or possibly u substitution, or possibly integration by parts. It's pretty infrequent that we would do a trig sub or a trig integral or partial fractions, but occasionally we might have to do one of those in order to evaluate the antiderivative. So you evaluate the antiderivative, apply the fundamental theorem, you do this part. All of that is just evaluating this part. When the fundamental theorem applies, you go ahead and apply it. Then the last part is to evaluate the limit. And as b goes to infinity, natural log of b approaches infinity very, very, very slowly. This area is infinite. I really want to get into the slow growth of natural log of b. Turns out if you put in like b equals, I think 10 to the 13th, natural log of that is only about 30. You might think that's not close to infinity. But this thing, it grows, and it grows very, very slowly. It's the tortoise, the tortoise and the hare. It's going to infinity, like it or not, it's getting there. But gosh, so slowly. You might say, well, how slow? What do you mean by slow? Well, remember what the rate of change of this is, right? You should know. You just took the antiderivative. The derivative is 1 over x. That's how fast this thing is growing. You say, okay, so what does that mean, Miss Townsend? I'll plug in an x value. How fast is it growing? What's the slope when x equals 100? It's 1/100th. That's tiny. That's 0.01. That's its rate of growth. X equals 1,000. 1 over 1,000. 1.001 is its rate of growth. So it's growing. It won't stop. It just keeps going and going. But my gosh, what a rate. That rate is approaching 0. It almost looks flat, but it's never quite flat. It just keeps growing at this tiny, tiny positive rate forever, and it gets to infinity. So turns out that this area under the curve is infinite. So now we've seen 2 graphs that look pretty much the same. I mean, at least on this little branch. On the interval, we looked at the interval from 1 to infinity of 1 over x dx. And we got, I'm going to write equals infinity going to put all of this in quotes because it even bothers me writing that. This is an improper integral, and it diverges. It diverges to infinity. And here, I've got an area, the integral from 1 to infinity of 1 over x squared instead of 1 over x, and it turns out to be 1. It turns out to be just a finite number. It's totally fine with us. Yeah, so there's not really any way of telling just by looking at the picture, like, is it going to be finite or not? Like, that looks like it might be finite or it might be infinite. This looks like it might be finite or it might be infinite. Actually, we can come up with a rule for like 1 over x to the p if we want to. And we might do that in another video. But I just wanted you to see, if you have a type 1 improper integral, you might get infinite area, or you might get finite area. You get 1, you could get infinity, you could get something in between. You might even get like a negative 17 if this thing dipped below the x-axis. So I'm going to wrap this video up, and we'll do some more examples in another video.